All right, this is a tutorial for the problem on page 65 of the workbook, which is part M, position plotting. And if you haven't listened to the lectures on position plotting yet, you should go back and look at those and try to do the example on page 64 with me in the video first. Then when you're feeling a bit more confident about how to do it, then of course the idea is we can do this one together. And you, of course, can pause me and try to do a little bit on your own and then see how I did it and then check your answers to see if you did a good job. Okay, so look on page 65, part M, question 1 at the top. It says plot a star with a declination of negative 20 degrees and a right ascension of 11 hours is seen by an observer at 25 degrees north latitude at a sidereal time of 15 hours. And you got the blanks here, just like I've got here. So first thing, let's go ahead and put a horizon on it. Just a nice solid line from cardinal point south to cardinal point north, first like so. And then give me a dotted portion of on the back as well, looking something like this. And there's our astronomical horizon. Okay, this looks awfully a lot like the example that we did together in the lecture. So these are the 4 quantities I need for position plotting. And they were given to me, but not in the right order, so that can happen, right? That sometimes the sentence structure is not quite exactly what you were looking for. But latitude is always dealt with first, and we'll color code this thing. Latitude was given as 25 degrees north. And in parentheses right here are the 3 quantities I can place because of my latitude value. North celestial pole, south celestial pole, and celestial equator. So if you're feeling confident about that, pause me right now and try to put those on there. Come back when you're finished. But if I've got 25 degrees north latitude, then my north celestial pole goes 25 degrees higher up than the north cardinal point. And if halfway up to the zenith is right about here, from north to the zenith, that's my 45 mark. And half of 45 is 22.5, which is about right here. And I need 25, which is, 3 hairs higher than that. So I'm going to say right here is my north celestial pole, NCP. And I'll label this angle so I don't forget. That's just always equivalent to the observer's latitude, so that's 25 degrees. Do the same on the alternate side. Starting at south, go halfway down to the nadir. 45 down is right here. Half of that is 22.5, which I believe is right here. And 25 degrees down, just like it was 25 degrees up on this side, it's 25 degrees down on this side, which is right about here. Label that the SCP. And label the angle one more time. That's a 25-degree angle. These 2 angles are always the same as the observer's northern latitude. All right, 1 down, 2 down. The third thing is the celestial equator, which is always going to be perpendicular to a line that connects these 2 poles. So it's going to look like this. And its meridian altitude, its height above cardinal point south, is always the same as the co-latitude, right? 90 degrees minus your latitude. 90 minus 25, 65 degrees. Starting at south, go halfway up to the zenith. There's the 45 mark. 3/4 of the way up right here is 22.5 higher than 45, which is 67.5. And I needed 65, so I need right here just a shade less than 3/4 of the way up. But I'm going to label everything. I got that by subtracting 25 from 90, or 65 degrees, the total height above. And we always do the same thing on the other side. So starting at north, go halfway down to the nadir. There's 45 down. There's 67.5 degrees down. I need 65 degrees down, right about here. Okay, label that as well. So this angle and this angle are always the same. And why do I have 2 dots here? To remind me to connect them. Solid on the front, a nice arc from here to here. Dotted or dashed on the back, a nice arc looking something like this. And what did I just draw? The CE. On the exam, it'll say draw and label everything. So be sure you label this. That's the celestial equator. I'm almost done with step 1, but I shouldn't forget to go back to the horizon and do what? Mark the other 2 cardinal points. East, where the celestial equator meets the front side of the sphere, right here. And west, where the back side of the equator meets the back side of the celestial horizon, right there. Okay, things are labeled, celestial equator, 2 celestial poles. I am done with the blue step, yes, or step 1 to do latitude. Okay, that's the most target-rich of the 4 steps, so you got to be able to do it or you can't continue as well, so it's important. Okay. Step 2 in green, the sidereal time. Got to look back, I've forgotten already. What's the sidereal time for this problem? The sidereal time is 15 hours. All right, let's write it up here. 15 hours, 15 to the power of h. And that's my reminder that sidereal time allows me to locate the VE, or the vernal equinox, the point from which right ascension begins. But I also remember that the vernal equinox is like a star. It's an invisible dot, yes, but it moves like a star does. And it's always confined to live on the celestial equator. And every day when the vernal equinox transits right here, we say that the sidereal day begins, and the sidereal time is exactly 0 hours. So 15 hours after it went through transit, how long does it take to go around entirely? Almost 24 hours, 23 hours and 56 minutes to be exact. But we approximate that 6 hours after transit, the vernal equinox has made it all the way to cardinal point west. If the sidereal time was 6 hours, I'd put the vernal equinox there, wouldn't I? 6 hours after that, the vernal equinox will make it all the way down to lower transit, crossing the anti-meridian. If the sidereal time were 12 hours, I'd put the vernal equinox there. But the sidereal time is 15 hours, 3 more than 12, which is exactly midway between the anti-meridian and coming back up again at cardinal point east. Really, just 1 tick mark is good enough. That's about where the vernal equinox should be, right here, in between 12 and 18. But if you want to make them nice equal tick marks back there, 1, 2, and 1 and 2 on either side of it to chop it up into 6 pieces, you could get there that way as well, couldn't you? 0, 6, 12, 13, 14, 15 hours. So if I draw my green angle all the way to here, I'll just remind myself that that green angle all the way around here is a 15-hour angle. That's how you say that. It's a 15-hour angle. And I located that dot. Who's that dot again? That's the VE, so don't forget to label it. That's the vernal equinox point. Okay. Yep, I'm done with step 2. It's much shorter than the first step. In the third step, I'm going to try to find my hour circle using the value of right ascension that was supplied. So let me look back again. Right ascension for question 1 on page 65 was 11 hours. And we're doing this in red, so okay, 11 hours, 11 to the power of h. And where do you begin measuring right ascension from? From the vernal equinox. It starts here. Which direction do you take sidereal time to locate the vernal equinox? It always goes to the right. Which way does right ascension always go? When you're inside the sphere, it always goes to the left. Right ascension and sidereal time always go in opposite directions. So I need to go 11 hours in the reverse direction, starting here. Well, if this is the 0 for right ascension, then count with me. 0, 1, 2, 3 gets me back to the anti-meridian. 6 more on top of that gets me to cardinal point west, which is a total of 3 and 6 is 9. I can draw that better. Again, I'm up to 9 here, and I needed 11, so I need 2 more hours, don't I, to make 11. Well, let's take this interval, this 90-degree interval from here to here, chop it in half. Give me 2 more tick marks equally spaced on either side. 1, 2, and 1 and 2. Just chopping this up into 6 pieces. And I was already at 9s. 3 and 6 is 9. 10 and 11 gets me to here. That red angle is an 11-hour angle. If I counted from here correctly, leftward, all the way to here. Give me a big dot right there. Now that's an aiming dot. I'm going to aim for it when I draw this. What are hour circles again? They're lines that go from celestial pole to celestial pole. South celestial pole to north celestial pole. Is that red dot I just made on the front side or the back side of the celestial equator? It's on the dotted part of it, isn't it, right? It's definitely on the back side. So guess what's going to be true of the hour circle? It's going to be on the back side as well. A line from this celestial pole to that celestial pole through that point and dotted looks something like this. Yeah? What did I just draw? That's the HC, the hour circle of the star. Every single object on that line has the exact same right ascension of 11 hours. Where on that line does it go? That's dependent upon the final value here, the declination. Okay. All right, step 4, take the declination, which in our case was negative, is it 20? Yeah, negative 20 degrees for the declination. Negative 20. And where do you start measuring declination from? It always starts at the celestial equator, but specifically, it's where the hour circle that you just drew intersects the celestial equator. Right here is where the declination is 0. Where the hour circle meets the celestial equator. And in this particular instance, it met on the back side, didn't it? So there's the 0. The SCP right here is where the declination is negative 90. And I needed negative 20. Halfway from here to here will be negative 45. And negative 22.5 is right here, midway between 0 and negative 45. And negative 20 is just about right here. I put a 5-pointed star right there and I say that angle from here to here, in my opinion, is 20 degrees below the celestial equator. There's my purple check. Forgot my red check from earlier. But those are the 4 steps of position plotting. And there's my sphere as it should look after those 4 steps are done. Well, how's yours look? Similar? What do you think? Is that star currently above or below the horizon? It's on the back, but it still is above the backside horizon, isn't it? Yes. So it hasn't quite set yet, but it's approaching. But that's part 1. Yes, or the sphere part of really, this problem. But you're right, there are more parts to it. So look below the sphere when you're ready. Part B, right below the sphere, says, next, estimate the current altitude and azimuth of the plotted star. Well, your plotted star is the purple star right here. And if you wanted to get the altitude and the azimuth of any star, what other device would you draw? Yeah, it's called a vertical circle, isn't it? And vertical circles always start at the zenith. They always come down through the middle of the object, the star, until they meet the what at right angles? The horizon. And because my star is currently on the back side, do we agree? Or to determine that, then my vertical circle is also going to be on the back side of this sphere. It starts at the zenith. It comes down like this, dotted line, right to the heart of the star. So it meets the backside horizon right there. That's just the vertical circle of the current position of the purple star. Well, vertical circles only have one purpose in life, and that's to aid me in helping to estimate the altitude and the azimuth. So what do you remember about azimuth? Azimuth is measured starting at the north cardinal point, isn't it? So that's what the azimuth is, 0, capital A for azimuth. Cardinal point east is where the azimuth is 90, always. South is where the azimuth is 180, always. And west is where the azimuth is 270. So do you agree that this vertical circle lands in between the 180 mark and the 270 mark? Do you think that it's slightly closer to west than it is south? Clearly I do. And this is 45 more than 180. 180 plus 45 is 225. So what do you like for the azimuth of the base of this vertical circle? I like a little bit more than 225. I like 235. And I would put in part B that the azimuth value, capital A, is, on the order of squiggle, about 235 degrees. Feel free to call yours 245 or 242 or 233, all in the ballpark. Even 225 is probably pretty close. And then what do you like for its altitude or its height above the backside horizon? Right where the vertical circle meets the horizon is the altitude of 0 right here. And the maximum altitude is the zenith on top at 90. So it's more than 0, less than 90. It's not even close to being 45 or halfway up, is it? Half of 45 is 22 and a half. I think it's even less than that. What do you think? 15? 20? 22? I'd take all of those. But I'm going to say that little h for altitude is on the order of, I'm going to say about 15 degrees. It's an educated guess. And even though the vertical circle, they didn't explicitly tell me to draw one, anytime that I need to estimate altitude and azimuth, I'm always going to draw one because that's my aid. That's what helps me do that. Okay, that was part B. Part C asks, next to draw the daily path of the star. Well, what do you recall about daily paths? Daily paths of stars are always parallel to the celestial equator. The celestial equator is drawn in blue right here. And the daily path of the star is, it's supposed to be a line that is parallel to the back of the backside celestial equator and parallel to the front side of the celestial equator. So I'm going to use the parallel finger method. I put a finger on where the declination is 0, and I put a finger on the star, and I keep that distance constant. What's the angle between my two fingers right now? It's 20 degrees. And if I ride the equator with my pinky like this, my index finger is tracing out the path of the star. It's going to transit about here. It's going to go through lower transit right about here, just keeping the 20 degrees below, constant. And what's a good color for that? I think I'll use purple, even though I've used purple a couple of times. But a line from its upper transit through the star to its lower transit here looks about like that, about parallel to the equator. And the front side of the daily path, I just got to wing that. It's going to look something like this. And clearly I do these a lot, so mine looks pretty good the first attempt. Don't worry, yours is going to look, pretty haywire when you do it the first time, but do your best. Try to keep it the same distance away, 20 degrees away. And I knew that the star's daily path should be the dotted path that goes to the star because I already determined that the star was on the back side of the sphere. If the star's on the front side, then the solid side of its daily path would be going right through the heart of the star. So just abbreviate it, daily circle, daily path, DP, DC, any of those are fine. And that was C. I'll just say check. I did it. I drew the daily path. Part D says, okay, now that you've drawn the daily path, then estimate the rising azimuth of the star. Well, I heard the word rising, and I kind of tuned everything else out at that point. How do I locate where the star rises on this drawing? Yeah, look at the front side daily path, the eastern side. Note where the daily path crosses the front side horizon right here. That is the rising point. To that point where the daily path crosses the front side horizon is the rise point. And you're correct, where the daily path dotted side crosses the dotted side of the horizon here is definitely the setting point. Okay, they want me to estimate the rising azimuth. Azimuth 0 at north, 90 at east. Do we all agree that the rising azimuth is larger than 90? Hope so. It's less than 180. If that's 90, midway between east and south is 45 more than 90, 135 degrees. What's this? 120, 115? Yeah, somewhere in that ballpark. I might say that the rising azimuth is squiggly, it's about, maybe 120 degrees, something like that. And look how, cluttered this is getting very quickly. I know, it's very dense. Thank goodness the sphere is pretty big. It takes up most of your page. But there are still 3 more questions to answer. Yeah, E, F, and G. But they're all just mathematical, which sometimes makes your life easier as opposed to harder. But part E says, all right, now that we know the rising azimuth, then calculate the setting azimuth. Do you remember this formula for setting azimuth? A little bit of algebra will tell you that it's 360 minus the rising azimuth. And 360 minus 120 is definitely 240, which you can almost estimate as being the same. Yeah, 270 is here, it'd be less than that, it'd be 240-ish is a pretty good approximation, but I can calculate it. I can get a hard answer, can't I? And then finally, F and G. Calculate the meridian altitude and calculate the hour angle. Well, just got to look back in your notes. For part F, meridian altitude, what's the equation? MA equals colatitude of the observer plus the declination of the object. Do I see colatitude up here somewhere? Colatitude is the height of the celestial equator, isn't it? That's the 65 degrees. There's the colatitude formula, 65. And plus the declination. What was the declination? It was negative. And you're adding a negative number, so it's the same as subtracting. 65 minus 20 is 45 degrees. Let's see if that checks. Did it come awfully close to hitting the midpoint right there where I marked it as 45? It came pretty close, didn't it? And for, drawing purposes, that's pretty good. Well, look how far we've come. We've done almost all the things that we've talked about in this unit to this one diagram. In the final step, part G, is calculate the hour angle. Do I really need to calculate it? What does hour angle tell me again? How long it's going to be, or how long it's been since the star went through upward transit? Well, I've already known that the star's on the back. You knew that too. How long has it been since my purple star was in transit up here? Go back up to the equator and count with me. Its hour circle goes to that tick mark right here. 1 hour, 2 hours, 3 hours. It went through transit 4 hours ago, didn't it? And that means the hour angle is it positive or negative? since transit. It's positive, right? Yeah. I'm sure hoping, because it looks like it's going to be positive 4 hours. Let's see if the math supports it. Hour angle, HA, hay equals straw. ST was it plus or minus RA? Piece of straw floating in the middle, remember? Yeah, it's minus RA. And my ST was 15. And minus my RA, which was 11. And, oh yes, thank goodness. Yeah, 15 minus 11 is definitely, erase that, is definitely positive 4, isn't it? I love it when it checks like that. The math and the literal interpretation of the diagram, you know, are synchronized, and they're the same. Whew. All right. That was a lot. And there's a lot going on in this unit. But you've basically taken everything you've learned in the unit and applied it to a single diagram. And it really forces you, again, to kind of know your definitions, and it really forces you to be able to understand what all different aspects of it mean. So it's a good summary kind of a diagram for the whole unit. Okay. Yep, that got complex, and that might be your first attempt, so don't let it daunt you too much. Rewind, go through each little piece of it, make sure that it makes sense. If not, shoot me an email. And guess what, we got more examples to do next, so we can see if you'll do those right too. Okay? All right, try that.